Welcome to this office mix, the second one looking at momentum, and this one covers momentum and elastic and inelastic collisions. What are we looking at in particular? We're looking at what an elastic and inelastic collision is. We're going to be comparing how the momentum before a collision and after collision compares when the objects don't join together, to move off separately, and we're going to be carrying out calculations for collisions where the objects move off separately after the collision. So, when two objects collide, their momentum is always conserved, but their kinetic energy may not be. So that is the law of conservation of momentum, that the momentum before is equal to the momentum after, provided there are no external forces. So momentum is conserved, but energy is not. If the kinetic energy is conserved, then it's called an elastic collision. So let's have a look here. So we've got a problem. The vehicle is traveling at 6 meters per second. It collides with another stationary vehicle, and after the collision, the vehicle moves off. The initial one at 2 meters per second, and the other one moves off at 8 meters per second. We have to show that the collision is elastic. So first thing we need to do is draw a diagram. So before, dotted line, and after. And we transfer our information to the diagram. The mass is 200 kilograms and 100 kilograms. The 6 meters per second of the first vehicle, stationary the second one, and then after the collision, the 200 one moves off at 2 meters per second. The 100 one moves off at 8 meters per second. Then the momentum before is equal to the momentum after. So before, m1 times v1 plus m2 times v2. So 2 times 6. So 200 times 6 plus 100 times 0 gives us 1200 kilograms meters per second. Now after, this problem is different now to the previous ones because they're moving separately. So we've got two terms on the right. 2 times 200 and 100 times 8. And we can see that the momentum is conserved because both before and after we have 1200 kilograms per meter second. So now we need to consider the energy to see if it's an elastic collision. So we work out the kinetic energy before and the kinetic energy after. The kinetic energy before consists of the two objects, one of which was stationary. So we've got half times 200, mass times speed squared, 6 squared, plus half times 100 times 0 squared. So we get 3,600 joules before. After the collision, we've got half mv squared plus half mv squared because we've got two objects moving. We substitute in the numbers, making sure we need to square the velocities, and then we get our answer. And we've shown it is elastic collision because the kinetic energy has been conserved. So as momentum and kinetic energy are conserved, this is an elastic collision. Let's now have a look at inelastic collisions. So an inelastic collision is a collision where momentum is conserved but kinetic energy is not. So now we're given a different problem. Car of 2000 kilograms is traveling at 15 meters per second when it collides head-on with another car of mass 1500 kilograms traveling at 25 meters per second. They lock together on impact and move off together. Determine the velocity and direction of the cars after impact, and is the collision elastic or inelastic? Justify your answer. That means do a calculation to show it. So we're going to do a calculation and show the kinetic energy before and afterwards. So there's two other points here as well. So we're going to draw out what's happening. So this time it's a head-on crash. So notice the arrow beforehand, one is going to the left and one is going to the right. Afterwards they join together and move off together to the right. So m1 v1 plus m2 v2 is equal to m1 plus m2 times v3. Notice the sign on the velocity here. So it's negative because it's going to the left, because it's a vector quantity. So we substitute in our numbers, we work out our values, we add them up. So 30,000 plus minus 37,000 gives us minus 7,500 equals 3,500 times V. So our answer is 2.1 meters per second and is actually traveling to the left. So even though our arrow at the top here is going to the right, because we've got a negative, that means it's going left after the collision. Let's look at the kinetic energy before and after. The kinetic energy is half mv squared, so we add up the kinetic energy of the objects before to give us a total, and then we add up the kinetic energy of the objects afterwards. And we can see that the energy is not equal, so it's not an elastic collision, it's an inelastic collision. Remember, in a collision, energy is always conserved. It's just that the kinetic energy may not be, because what's happening is that energy is produced in terms of heat and sound. If we think of a car crash, how do we know there's a car crash? Well, we know there's a car crash because we can hear it, bang, and the metal has work done on it, which means it squashes. So most collisions in reality are inelastic, and some of the kinetic energy is converted to heat and sound upon impact. So you need to know what an elastic and an inelastic collision is, how the momentum compares before and afterwards, momentum is conserved, and to be able to carry out calculations for objects that join and for objects that are going in opposite directions.